I will start about DC-DC converter. So before starting DC-DC converter, you must know why we should study about DC-DC converter. What is the requirement of DC-DC converter? Because nowadays in every electronic component they require the DC voltage. In our laptop also require DC voltage to charge this laptop, and also in our mobile require the DC voltage. And this charging level, voltage level is the different for the different device. For mobile charger it is require the 5 volt, for laptop charger it require 12 volt. Different voltage level is required. So in AC voltage we can change this voltage level very easily by using transformer. By only change the number of turn, we can easily change the output voltage. So in transformer, by changing number of turn on the secondary, we can change the output voltage as our requirement. But in DC voltage, it is not possible by changing the number of turn or by using the transformer. That's why we use here different type of switch. So to convert DC to DC converter, we use different type of power electronic switch. So that can change the voltage level. Actually, DC-DC converter is a power electronic converter that convert DC voltage level, one DC voltage level to another level. Right? So that's why we use DC-DC converter. So here we can use power electronic switch. So this power electronic switch can be operated in the 3 regions: active region, cutoff region and saturation region. By using their region, we can classify it as 2 types. One is called linear region and another is called switch mode DC-DC converter. So linear active region means the linear voltage regulator. Linear voltage regulator where we use this switch, power electronic switch, and this switch must operate in active region or called linear region. By only using this switch, we can also control the output voltage. And another method is that in the previous case we use this DC voltage by using the simple resistance. So here the DC voltage, suppose one DC voltage is 10 volt and here is the load is there. So in this load is required 5 volt. How it is possible to get 5 volt? By using one extra resistance. If we add here extra resistance, there must be some voltage drop, then the remaining voltage we can obtain here. If we use this resistance, power loss will be occur due to using resistance. That's why we use here the switch, only the power electronic switch. So here we use power electronic switch. In this switch, we can control the output voltage. How it is possible? So this only possible by change this base current of this transistor. So here the supply voltage is there and here the output voltage. It is record output voltage across this load. And the current through the load is called IL, load current, and the output voltage is V0. So we can change this voltage as our required by only change this base current. So this type of regulator is called linear voltage regulator because this switch operate in active region or linear region. They also have some disadvantage. What is the disadvantage? So here disadvantage is that some voltage drop occur across this switch also. When it will be on and it will be off. What will be happening there? So the transistor is effect operate as a variable resistance, and here the efficiency will be reduced of the switches. Why efficiency will be reduced? Because some power loss occur across the switches. Clear? Some power loss occur across the switches. That's why how we reduce this loss and improve our efficiency. So we reduce this loss and also improve our efficiency by using here switch mode DC-DC converter. Switch mode means here we use this type of component or the switch which can operate only on and off. This mode means cut off and saturation region, no active region. So by using this region we can reduce these losses. And we can our assumption is that this switch must be ideal switch, but it is not possible. So there must be also some voltage drop will be there, some power loss will be there, but it is very minimum. So we can improve our efficiency by using a DC-DC converter, switch mode DC-DC converter. Now the basic switch converter, look here. So basic switch converter, what is there? Simple, supply voltage is there, Vs, here we provide the supply voltage and here is the one switch and here the load is connected. So we can get the output voltage across this load, V0, we can get the output voltage across this load. So when switch will be on, then what will happen? Output voltage will be same as the supply voltage. When switch will be on, when switch will be off, the output voltage will be 0. V0 will be 0. By on and off, we can get the output voltage. So by on and off, when switch will be on, we can output voltage as a Vs, it will be V0 will be Vs supply voltage. When switch will be off, we can get output voltage is the 0. Again, when switch will be on, we can get output voltage. Again, off, output voltage will be 0. So here we can get a pulsating DC, not a constant DC. It is a pulsating DC. So our aim is that how we convert from this pulsating DC to constant DC. How it is possible? So it is also possible by using a chopper circuit. Chopper means chop. So here we use a switch which can chop. It's a high frequency operator. It will be on off, on off, on off. That's why it is called the chopper. Clear? Look here. So for our assumption is that this switch must be in the ideal. So here the ideal switch is there. When switch will be off and the on, according to on and off, we can get the output voltage. So when switch will be on, we can output voltage and supply voltage. When switch will be off, output voltage will be 0. Again on, again off, again on. So we can get a pulsating DC. And this is called the time period T, the total time period T. And we know the duty ratio D is equal to T on by total T. What is the T? It is a time period. Time period means T on plus T off. So here we can say T on by T on plus T off. It is called the duty ratio. So from this equation, we can calculate the T on. So T on is equal to T into T. So here we can say this is the on time period, on time. So it is on. So here time is called dt. And the total time period is the T. So the remaining part is T minus dt. It will be the off time. So T minus dt. So here T will be common, 1 minus D. So this will be the 1 minus D into 2 is called the off time. So this is off. Clear? So it is called duty ratio. D. D is called duty ratio. T on by D. So from here we can calculate on time and also off time. So when switch will be, look here, when switch will be the on, output voltage will be same as supply voltage. When switch will be off, output voltage will be 0. So if we take here average voltage, then we can get the output voltage equation. Because V0 is equal to 1 by T, total time period, integration 1 to T, V0 T into dt. So here V0 is equal to Vs dt. Where it is possible? When switch is on. That's why I give here the on time dt. Clear? When switch will be the on. So here this is the dt, on time, and here the off time is 1 minus d into t, and the total time period is t. So that's why the simple equation. So from this equation, we can see that output voltage is equal to Vs into d. So output voltage depends upon supply voltage. Output voltage depends upon supply voltage Vs, and with d, duty ratio. If we change this d, duty ratio, we can get the different output voltage level as our requirement. So we can change here voltage as our requirement by change only duty ratio. It is in our hand. We can control it. Clear? Now we have the D duty ratio. And in this equation, we can say T1 by T, D is equal to T1 by T. So 1 by T is frequency also. So D is equal to T1 to F. F is the frequency. Now, come here, it is called the buck converter or the step down converter. Means where the output voltage will be less than input voltage as similar to transformer. When output voltage is less than input voltage, we can say it is a step down transformer, and here it is called step down converter because output voltage is less than input voltage. When output voltage will be more than input voltage, it is called step up converter or called boost converter. Well, the two is possibility, down and the up, then it is called buck boost converter. According to their working principle, we can change it. So here at first you must know about the DC-DC buck converter, or it is also called the chopper, because here we use this switch, power electronic switch. This power electronic switch should be operate as our switching frequency on off, on off, on off. That's like a chopping. That's why it is called the chopper. Nothing else. So here in the buck converter, simple circuit. So here we use on switch, and here this is the output voltage, the load is. So we can get the output voltage across the load, V0. We can get here. So we can get, but if you use only the normal, use the only switch and only output voltage, so we can get the output voltage. This output voltage like a pulsating, DC, not the constant DC. So how we get this constant DC? So we can get this constant DC by using normal and low pass filter. So this inductor and capacitor are only used for the filtering purpose to get pulsating DC to constant DC. And here we use the one diode. Why we use this diode? So because whenever you go for the working principle, then you can understand why we use this diode. So what is the working principle here? A simple thing. When switch is on, then what will happen? When switch will be on, when switch is the on, that is the short circuit. So current will flow through this path. And this diode can't flow in this way because here we use the one diode. So this diode will be the reverse bias. So that's diodes like an open circuit. Reverse bias, so it is the open circuit. And here current will be flow in this path. So there is a two way to flow the current. Either the load and the capacitor. And then when switch will be off, then what will happen? Switch is off. So it will be open. So open from the supply. Then when switch on, it is stored in the inductor. So this stored energy want to release through this load. So how it will be released? So it will be released. That's why here we use the diode. This diode should be the forward bias. So this stored energy can be released through the load and through this diode. If we don't use here the diode, then what will happen? Then no way to release this path. We use here the diode. That's why we use here the diode. So when it will be switch is the closed, so this diode acts as a open circuit. When switch will be open, this diode acts as a forward bias. So current can flow. The stored energy of the inductor can be released through this diode and through the load. That's why we can get the constant output voltage. And here this voltage can be increased or can be decreased by only change this parameter, change this duty ratio. And this circuit is called buck converter or a step down converter because the output voltage is less than input voltage. Simple circuit, nothing is here, very simple. And in this lecture, we can also design a buck converter. What will be the required of this inductor value? Minimum inductor value is required, and also the minimum capacitance value is required. So we can design what will be the minimum frequency is also required for a particular voltage. Suppose our input voltage is 20 volt, our required voltage is suppose 5 volt. So we can get this 5 volt only by change the duty ratio. So in this 5 volt also, what is the required value of this inductor and the capacitor? We can design here. What will be the value? And our assumption is that this inductor current should be remain positive throughout the switching period. It is known as the continuous current. So inductor current will be continuous process, not the discontinuous, not will be the zero. It will be continuous. This is our assumption. And another assumption is that the switching element, the switching circuit, that what about the switch? This switch will be the ideal case. Got it? So now, before starting the circuit analysis, some assumption is required. What is the assumption? We can take a sum making this assumption. So the first assumption is that the circuit is operating in the steady state condition. In the steady state condition, the inductor current is continuous, always positive, not discontinuous. It will be the continuous result. And this capacitor we use as for the filter purpose. This capacitor must be very large. It must be very large. And the output voltage is held constant at the voltage V0. So output voltage will be kept constant when use a large capacitor. And the switching period, we already know the switching time period is the T. When switch will be on, so this time is called dt. And when switch will be off, this time period is 1 minus d into t. And this component, all this component are in ideal. So this component must be ideal. And then to analyze this output voltage, we must first consider as a inductor current and the inductor voltage first. So inductor current means the net change in inductor current over a time period, it must be 0 for steady state operation. So the net change in inductor current over one period, it must be 0 for steady state operation. So upon this assumption, we analyze this circuit and we will see that what will be the output voltage, and the last is the average inductor voltage is 0. By using this net change in inductor current and average inductor voltage, we can calculate this output voltage. What will be the output voltage? So see, analysis of the switch close. When switch will be the close, then what will happen? So at first I draw here the circuit. So here the switch is there, I have the supply voltage and diode and the inductor or capacitor. This is the load. So when switch will be closed, it will be the close. Then what will happen? Current will go through this supply and this diode acts like a open circuit. Okay, reverse bias condition. So this diode acts as an open circuit. This diode acts as an open circuit. So current can flow through the inductor, through the load and the capacitor. So what will happen? We can see here the voltage across inductor. What will be the voltage across inductor? It is called the Vn. So here the supply voltage is Vs and output voltage is V0. So the voltage across inductor VL will be Vs minus V0. Very simple. So here the voltage across inductor Vn is equal to Vs minus V0. Then what is Vn? Voltage across inductor. So voltage across inductor means L di by dt. So here the voltage across inductor is the net change in the current. So the L inductance into dIL by dt is equal to Vs minus V0. So from this equation we can calculate dIL by dt is equal to Vs by V0 by L. Vs minus V0 by L. Just we rearrange this equation. Okay. So at first we calculate the voltage across inductor VL. VL is equal to Vs minus V0. So what is Vs? Vs is equal to voltage across inductor. Then we can say VL is equal to L di by dt. Okay. And from here we can calculate dIL by dt is equal to Vs minus V0 by L when switch is closed. Now when switch is closed, at that time what will be the time? At switch is the closed. As I previously told, when switch this time period is called the T, total time period, and it is the on, and here switch will be the off. So this time is called dt. When switch will be the closed, and when switch will be the open, this time is called 1 minus d into t. Clear? So I just put here this time period dt to here. I just rearrange this equation. So here dIL by dt. So del IL by dt. So this dt del t the changing time. So this time is the on time. What is the on time? On time is the dt. I just put here the dt. And from this equation we calculate this del IL, change in inductor current. So this del IL close is equal to Vs minus V0 by L into dt. So This is the net change in the current when switch is closed. Now we analyze this when switch will be open. Then we know our assumption is that the net change in inductor current must be 0. So this inductor current for the closed and for the open, if we summation these two, it will get the 0. So just we will do it, then what will be the result? We will see it. So in previous slide, we see the analysis of the switch when switch is closed. Now, the analysis for switch open. Switch open means when the circuit had this switch must be open. So when switch is open, then this diode, inductor, and the capacitor, and the load. When switch is open, this energy is stored in this inductor. So this stored energy can be released through this load and through this diode. So this diode will become a forward bias. So current can flow through this part. So when switch is open, so in this condition, so this time is called switch is on and here switch is off. And this off time is called 1 minus D into T. And then the total time period we know is the T. So when switch is open, at that condition, the voltage across inductor, VL, when switch is open. So this stored energy of this inductor can discharge through this load. So the voltage across inductor will be decreased, and it is the same as the output voltage V0. As this voltage will decrease, so we can say it is the VL is equal to minus V0. And this inductor voltage will be same as output voltage. And here as this voltage will be decreasing, so we can say VL is equal to minus V0. Again we know voltage across inductor is equal to L di by dt in terms of inductor current change. So L di by dt. So from which is rearrange this equation. So L di by dt is equal to minus V0. So from here we can calculate dil by dt is equal to minus V0 by L when switch is open condition. And when switch is open, at that time what is the time? Time is 1 minus D into T. In place of the dt, we just put here this time of the switch. So off time of the switch is 1 minus D into T. I just rearrange this equation. And here put del IL by 1 minus D into T is equal to minus VL by V0 by L. And from this equation, we can calculate only inductor current, change in inductor current. So del IL open, at the open condition when switch is open, so we can say this equation is minus V0 by L into 1 minus D into T. So it is for inductor current change for the open condition, switch is open, and again we calculate in previous case when switch is closed. At that time we also calculate del IL close. Then we know for the steady state operation, the net change in inductor current must be 0. What does mean? This means that inductor current at the end of the switching cycle be the same as at the beginning. So inductor current will be same from the ending of a complete period. So net change in inductor current must be 0. Then we know inductor current when switch will be closed and when switch will be open. So this net current will be 0. So that's why I just put here this inductor current closed and the open is equal to 0. And then what is the inductor current when it will be the closed? So this equation for inductor current when switch is closed at that condition, we calculate this equation del IL closed. So it should be the Vs minus V0 by L into dt means the on time. And when switch is open, so this time is 1 minus D into T, and here the voltage will be decreasing. That's why I just write here minus V0 by L. So if we add these two equations, we can get the output voltage here. Just rearrange this equation and then calculate the V0. So V0 will be Vs into T. So from here we can get the output voltage. So this output voltage, from here you can see that here also the output voltage depends upon the duty ratio. This is another process to prove it. So V0 is equal to Vs into D. What is Vs? Vs is the supply voltage and D is the duty ratio. So this proof is only by the change in inductor current. Also this can be proved by changing inductor voltage. So by using the voltage, also we can prove it. The V naught output voltage is equal to supply voltage into building AC. How it is happening? So based on the inductor voltage. So we know when switch is the closed, what is the inductor voltage? When switch is the closed, what is the circuit? At first I just redraw the circuit. So here the switch and here the diode, the supply voltage, inductor, capacitor, and there is a volt. This is the circuit. Clear? So when switch is closed, then what will happen? When switch is closed, then what is the voltage across inductor? The voltage across inductor is the inductor L, capacitor C at the load. So here the voltage across inductor VL, VL is equal to Vs supply voltage, this is the supply voltage, and here the output voltage V naught. So we can say that Vn is equal to, when switch is closed, is equal to Vs minus V naught into time period. So this time is dt. When switch is the closed time, it's all the dt, and here 1 minus d into t. Clear? So from here we can take this voltage. So when switch is closed and when switch is open, this is the voltage across inductor. So if we add these two, we know the net inductor voltage must be 0 complete for a one complete period. So here we can say just add these two, we can get the 0. So from this equation, if you rearrange this equation, you can get here the V naught is equal to Vs into T. So also we can prove in the theory. One is the average voltage, and then by using net inductor current, and here by using based on the inductor voltage. By three process we can prove it. What is the output voltage equation? So for DC-DC buck converter, output voltage V naught is equal to Vs into D. What is D? D is duty ratio. What is D? You know, this is the ratio equal to T on total time period. So from here we calculate the T on time is equal to D, and the off time should be T minus dt. So we can get the output. For the switch is closed, so here the time period time will be 1 minus d into t. So by using a simple equation, we can prove here what will be the output voltage for a buck converter. Now, for a designing purpose, what will be the required inductor value? What will be the capacitor value? What is the minimum inductor is required? So this circuit will continuous process. So this circuit will operate in continuous mode. So this inductor value is a critical inductor value, and this capacitor value is also called critical capacitance value. So we can also calculate by using this equation. Let's see what will happen here. Now we calculate the value of IN, inductor current, or it is called the load current. So both will be same. So what will happen here? The average inductor current must be same as the average current of the load resistance. So current will be same. Why current will be same? Now again, if we draw here the circuit here, so the switch, supply voltage, the supply voltage Vs, and here the V naught. Inductor, capacitor, this is the diode, here it is the switch. Now the value of the IN, so current when switch is closed, current will flow through this path. So this current is the same as the load current also. Some current will flow through the capacitor part. Here we assume that this capacitor current is very minimum, so we can neglect it for the steady state concept. Alright. So here the average inductor current must be same as the average current of the load in the load resistance. So here we can calculate the IN. IN is equal to IR. Same load current is equal to resistance current. If you have put on the resistance, so it will be same. IL and IR will be same, is equal to, we know current is equal to V by R. So V means your output voltage V naught by resistance R. So if you put here one resistance, then we can calculate this one. We know V is equal to I is equal to V by R. So what will be the voltage here? Output voltage V naught and the load resistance R. So from here we calculate I. Then we calculate I max. What is I max? If you look about the current, inductor current, then if you look about the inductor current, then what will happen? Inductor current. When switch is on, where it is on, say, adapter switch is closed and where switch is on. So this is called I minimum current, and here this current is called I maximum. Here I maximum. So this is the del I, net change in the current. Del I, net change in the current. So this is the difference between I minimum and I maximum. If we take the average current, so here it will be the average current. Got it? So how we calculate this I max? How we calculate this I max? This I max is equal to IL, load current or average current, plus if this total deflection is del IL, so it will be the half, so del IL by 2. Clear? So total deflection is del IL. Got it? So it is the del IL. So here it is the total del IL. So the half will be del IL by 2. So here it is the del IL by 2. So if I add here the IL, load current plus del IL by 2, so we can get the I max, maximum current. What will be the maximum current of the inductor? Got it? And then we can also calculate the I minimum inductor current. How we calculate it? We calculate it. We know the IL, average load current, IL from here. We know the IL. So from this IL, if we IL, so it will be del IL by 2. Del IL by 2. So from this IL minus del IL by 2, we can get here I minimum. So from this equation, we can calculate I maximum, also I minimum by the simple equation. We know the IL, load current. So just put here the IL plus del IL by 2. Why del IL by 2? Is it clear? So because it is the load current and it is the maximum. So total deflection is the del IL. So half will be del IL by 2. So if we add IL plus del IL by 2, we can get I maximum. So here I maximum here. I maximum is IL plus del IL by 2. Now what is that IL? Load current. Load current is equal to V naught by R. Just from here V naught by R. I just put here V naught by R. Then del IL by 2. So 1 by 2. Just put here. Then what is the del IL? Net change in inductor current. I take here the off period. So off period means 1 minus D into T. And here the del IL. So what is the current will be del IL? So it will be the V naught by N in the previous case. You see it when switch is the off. At that condition, what will be the voltage? So just put here. And from this del IL. So I just put here the del IL value. Just put here. And then from this equation, if we add these two, we can get the I maximum value. So I maximum will be V naught into 1 by R plus 1 minus D by 2 LF. What is F? F is the frequency. Clear? F is the frequency. So from the time period, we can see what is the frequency is equal to 1 by T time period. So in place of the time period, we put here the frequency. So here we can calculate this I max. According to same, we also calculate I minimum value. What will be the minimum value? IL minus del IL by 2. The equation will be same. I just put here the minus because we want to calculate this I minimum value. So it is the IL. So IL minus del IL by 2. We calculate I minimum. Just put here this IL value. So we can calculate I minimum. So what will be the maximum current and the minimum current? So we can easily calculate it by using this IL. So from this equation, we calculate I maximum and the I minimum. Then the remaining part is inductor and the capacitor. So how we calculate this inductor value? So what will be the minimum inductor value? So we can get this equation, this solution will become in continuous process, in the continuous. So the L minimum, what is the value of the L minimum? It is also called the critical inductance value. How we get it? So we can get by using the I minimum value. So below this inductor value, the current will be discontinuous. The system will be discontinuous. So our aim is that the system must be in continuous process. So it cannot be below the I minimum value. So here the minimum, here the main, our aim boundary is that I minimum should be 0, not below the 0. So if I put here the I minimum 0, then we calculate the inductor value. I just put here I minimum is equal to 0. What is I minimum value? In the previous slide, we can see that what is I minimum. So just put here this I minimum value and is equal to 0. From here, we can calculate the inductor. So in this equation, we can calculate the L minimum. So this is for the continuous current. Below this L minimum, critical value of this inductor, current cannot be in continuous current. It will be discontinuous. So our aim is that our circuit should be in continuous current. Right? So here we calculate L minimum. So only by using the I minimum current. So if we put I minimum is equal to 0, we can get here the L minimum value. Clear? And then determination of the inductor L minimum. I just put here this equation. I minimum value is equal to 0. So just put this I minimum value is 0, then we can calculate here the L. So from this L, you can see here, it is the F is the frequency. So if we increase the frequency, inductor will be, value of the inductance will be decreased. So that's why in this circuit converter, DC-DC buck or the boost converter, we operate this at a high frequency. Why? Because this inductor value will be reduced. So inductor size will be reduced. If inductor value is reduced, inductor size also will be reduced. It will be in the compact in size. That's why this maximum circuit, we want to try and operate in a very high frequency, in the kilowatt range. Kilohertz range. The frequency will be in a kilohertz range. Kilohertz to megahertz. That's why we use that type of the switch, electronic switch. We use here the MOSFET, IGBT. We use, clear? So we can calculate here the inductor, L minimum value. And also we can calculate here the capacitor. How we calculate this capacitor value? So before calculate capacitance value, you must know the power. So since the converter component, we can say the input power is equal to output power. What is input power? Input power is voltage into current. I just supply voltage into supply current is equal to output voltage and output current. So from here we can say V0 by Vs is equal to Is by I0. Therefore the buck converter circuit is equivalent to a DC transformer. It is the same as the transformer circuit. V1 by Vt is equal to I2 by I1. We know the transformation ratio in the transformer. Got it? So V1 by Vt is equal to I2 by I1 is equal to N1 by N2. It is called the transformation ratio. And here also you can see that the input voltage by output voltage is equal to input current by output current. That's like a transformer. That's why we can also say that the buck circuit is the equivalent to DC transformer. Now the output voltage ripple. So it is the output voltage IC current. What is IC current? Now again, if you look the circuit, then you can see that inductor, capacitor, the supply voltage. So here the current switch is the closed. Current will flow through the inductor, and some current will flow through the capacitor, and here some current is the load IL. So we can say here, suppose it is the IL, and here it is called the I0. Then what will be the IC current? IC current will be I0 minus IL minus I0. IC current will be IL minus I0. We can get this IC current. So here this is the graph of the IC current. So it will be at first energy will be stored here. The capacitor, when switch is the closed, some current will flow through the capacitor. So capacitor will charge the energy. Got it? When switch is the closed, it will to the discharge through this path. So the output voltage remain constant. Got it? So this capacitor only used to get the constant output voltage, not the pulsating DC. Constant output voltage. That's why the assumption is that we use a large capacitance. Clear? So here we use this capacitor. So here IC is equal to IL minus IR. And here from the definition of the capacitance, we know Q is equal to CV. C into V0. Here the V means the V0. So here the del Q is equal to C del V0. And the del V0 is equal to from here del Q by C. We know it. Del V0. Change in the voltage, output voltage. Change in the output voltage is equal to del Q by C. So here it is the IC current. What is IC current? We know IL minus I0 or the IR. So if you look here the I0 IL current, so you look at the IL, and if you divide it, if you subtraction by I0 or the IR, then you can get the IC current. So IC current will be looked at. So here is the store energy, and here it will be the discharge. What is the charging and the discharge? And here the del Q. So if you look here, so this is the total one time period. It is the one time period. One time period. here it is a one time period. So if this is the one time period t, total time period t. So in the total time period there must be on time and the off time. So the half of here, look here, the half of the store energy and the remaining half is the discharge energy. Got it? If we take the area, so we can say here del Q is equal to half into T by 2 into del IL by 2. So from this equation you got the del Q. Del Q is equal to T del IL by 8. So from here we can get the output voltage del V naught. Change in the output voltage of the capacitor. Got it? So here we can get the output voltage. So from this equation we calculate this capacitance value. So what will be the capacitance value from this equation? Easily calculate what will be the capacitance value. Again you can see here this capacitance value also depends upon the frequency. Clear? Also depends upon the frequency. If you increase the frequency large and large, the capacitance value will become less. So that's why to get the compact size, a converter, so our frequency should be very high range. So we can design a buck converter. So if our frequency is known, then we can calculate the capacitance value. We can calculate the inductor value also. What will be the minimum inductor value? What will be the minimum capacitance value? We can calculate from here. So each and every parameter for a converter, buck converter, is calculated. Supply voltage Vs. So this is the switch, our electronic switch. We use here the MOSFET, IGBT as our requirement, and here the diode, and we know the inductor value, we know the capacitor value. So each and every parameter is calculated here. Any question? Okay, thank you.